Hi everyone, my name is Pritha Paul. I am currently a postdoc at Queen Mary University of London and I am working with Chris Clarkson and Roy Martins. Thank you all again for giving me the opportunity to talk in the Parity Violation from Home conference. Here I will be speaking about the parity-odd trispectrum, and also I will go into a bit more details about how to visualize these effects that gives rise to this parity-odd observed trispectrum in redshift space. So I would like to start off with understanding what our galaxy surveys really measure. So we're currently in an era where we have many current and upcoming galaxy surveys, and it is important to stress that these cosmological observables that we have, they are defined on our pass light cone, the pass light cone of the observer. As a result, effects such as the redshift-space distortions, relativistic effects, lensing, they all enter into what we actually observe. So here I have a plot that shows a spherically symmetric density contrast of an isothermal sphere. In this particular plot, we have a central overdensity that slowly falls off with the radius. And when we observe in redshift space, we don't observe the true dark matter fluctuations. Instead, we have several effects that distorts this spherically symmetric sphere into all sorts of different shapes. So mathematically, we can write down the observed galaxy number density. And Kaiser showed that the observed galaxy number counts, they are not just affected by the underlying matter distribution. Instead, we also are affected by this radial derivatives of the peculiar velocity of the galaxies. So this is denoted by the Kaiser term. So the first term we have B delta, where B is the galaxy bias, and your d chi v parallel, which is representative of the Kaiser term. It's the radial derivative along your line of sight peculiar velocity. Here, v parallel represents v dot n, where n is your line of sight. On this plot, this is the visualization of a Kaiser term for an isothermal sphere. This has been done in literature before, and we know that the Kaiser term distorts any overdensity into an ellipse. So on the far side of the overdensity, galaxies are moving towards the observer, so their spectra are blue shifted, and as a result they are pulled inward, while on the near side the galaxies are moving away from the observer, so the spectra is redshifted and it's pushed outwards. And both of these effects combine together to move the edges towards the center in redshift space, making the object appear compressed along your line of sight. However, this is not the full picture. We also have the Doppler contribution, which is a term that is proportional to just v parallel, which is equal to v dot n. And this term is suppressed with respect to the Kaiser term by a factor of h over k in Fourier space. As a result, they become relevant as we go into larger and larger scales, or smaller values of k. The Doppler term on the right is very different to the Kaiser term. So that visualized is not symmetric along the line of sight. Instead, it has a dipolar shape with an overdensity on the right and an underdensity on the left. Here, I am showing the Kaiser term, which is added onto the isothermal sphere. So the overdensity is compressed along the line of sight into an ellipse. The plot on the right shows the Doppler term added to the Kaiser term as well. So the Doppler term is magnified by 50 as it is suppressed with respect to the Kaiser term by h over k. However, when magnified by 50, it results in an asymmetry along the line of sight and a centroid shift as well. We can now use the galaxy number counts to construct statistics such as the power spectrum. The power spectrum is usually our statistic that is used commonly in literature. From this plot of the power spectrum, we can see that there are lots of constraints on the equality scales, but fewer as we go towards smaller values of k or larger scales. However, with the current and upcoming surveys, we plan to get much more data on the larger scale, so it is becoming more and more important that we take account into these effects that dominate these scales. Alongside the power spectrum, it is also important that we now look into statistics which are beyond the power spectrum. So we have the power spectrum here, where the power spectrum considers two galaxies. So in Fourier space, we have delta of k1 and delta of k2 to give us the power spectrum with the Dirac delta function. We can go a step higher, and we can, instead of counting pairs of galaxies, we can now count triplets of galaxies. In this case, in Fourier space, we have delta of k1, k2, and k3, which gives us the bispectrum with the Dirac delta function. One can also go an even step further to the trispectrum. So instead of counting triplets, we can now count tetrahedrals of galaxies. In Fourier space, this would manifest as a quadrilateral, and we now have delta of k1, k2, k3, k4, giving us the trispectrum with the Dirac delta function. An additional motivation for us to work out the trispectrum was also the detection of a parity-odd 4-point function by Jamin Hu, Zach Slepian, and Bob Kahn. They performed an analysis on the luminous red galaxies of the BOSS survey, where they found 3.5 sigma evidence and 7.1 sigma evidence, respectively, for two sets of data for the LOES and the CMAS. I do want to point out, though, that in this particular analysis, they have averaged over all lines of sights, and unless there is any contamination from the window function, this particular relativistic effects would only come into play for the dipole of the trispectrum, while they have worked out the monopole in this case. We will now have the theoretical setup for the trispectrum. We can construct the trispectrum by correlating four density fields. In this case, we have delta G of K1, K2, K3, and K4, where G represents the delta in redshift space. This gives us the trispectrum and the Dirac delta function, which poses homogeneity. And in order to work the trispectrum out, we have to go to the density field. We have to expand perturbatively the density field to second and third order. So if we just have the first order kernel in K, then we will get no more information than we would do for the power spectrum. As a result, it is important to go up to second and third order in density field for the trispectrum. So at tree level, we can write down the trispectrum in terms of the two contributions. One is the third order contribution with 4 cyclic permutations in K. In this particular case, the cyclic permutation is in K4. And we also have the second order contribution with 6 cyclic permutations. So these are in pairs of permutations of K1 and K2, swaps with K3 and K4, and vice versa. So each of these kernels, we can break them down into two parts. One is the Newtonians, the standard Kaiser terms, and the other one is the general relativistic term. So the standard Kaiser term is what we have seen in standard trispectrum analyses, while the relativistic terms in Fourier space is new. So the second order kernel has been worked out before. However, a key thing to note in the second order kernel is that it is in even powers of mu. So each of the second order Newtonian kernel is symmetric along your line of sight. Mathematically, we can see it with each term being even powered in mu. Visually, we can also see that. So here I have shown the second order terms visualized for an isothermal sphere. The top right contribution is the total second order Newtonian contribution, which has symmetric contributions along the line of sight. However, all the individual contributions at second order, they also have symmetric contributions along the line of sight as well. Moving on to the second order relativistic kernel, which has also been worked out before in literature. It is the key thing to note here mathematically that each of the terms here are odd powers in mu. So when you have a change in k, so when k goes from minus k, you end up with this asymmetric contribution. Visually, we can see it here as well. So instead of all of the terms being symmetric on both ends, now the second and third rows, the first and the second row are representative of the individual relativistic terms, and the top right panel shows the total second order relativistic contribution. But all of the terms, the individual terms and the total terms, are both asymmetric along the line of sight. Some form a dipolar pattern, some form more of a butterfly pattern, but both show an overdensity on one end and underdensity on the other. Moving on to the third order kernel, the math remains exactly the same in terms of the fact that for the Newtonian third order kernel, mathematically it is also symmetric along your line of sight because you have all even powers in mu. However, if you move on to the third order relativistic kernel, the number of terms increase by a fair amount. However, the intuition behind all of the terms is same as they are all odd powers in mu. So if we had to construct an odd trispectrum, this third order GR kernel and second order GR kernel would represent the asymmetric contributions. We now move on to constructing two T-even and T-odd. T-even is the parity preserving part, so when k goes to minus k. And T-odd is the parity-odd part. So it's the part that will isolate the parity-odd contributions. Taking these functions T-even and T-odd, we now plot these functions. So on the x-axis here is the wave number k. On the y-axis you have the T-odd and T-even. The odd is represented by the dashed line, while the even trispectrum is represented by the solid line. They are for two geometries. One is Euclid, which is the black lines, and the other one is SK intensity mapping like survey, which is the orange lines. The geometry is shown on the quadrilateral on the plot. We have also shown the geometry of the trispectrum just in general. So here we have fixed all the other angles. Big theta and big phi are the configuration angles, and small theta and small phi are the viewing angles with respect to the line of sight vector n. So the key thing from this plot is that as we go to larger scales, so as we move past the equality scales, we see that the odd trispectrum takes over for both the Euclid and the SKA-like survey. So it is important as we go up to higher scales, we ensure that we are taking into account these effects. We also did a bit more investigation because it was very, the T-odd and T-even depended heavily on the kind of configuration of the quadrilateral. As a result, we plotted this ratio of the odd to even trispectrum for an SKA-like survey as a function of configuration angles. This was at k is equal to 0.01 H inverse megaparsec. For all the configurations, the relativistic corrections are 10% or more. The bright yellow parts are nothing interesting, except it's a mathematical divergence, so it's just where the even part changes sign. However, the key thing to take away from this plot is that all contributions of the T-odd is 10% of T-even. We also plotted something very similar, except now instead of using the configuration angles which determine whether the quadrilateral is squeezed or the quadrilateral is different shape, we now take into account small theta and small phi, which are associated with the viewing angles. Even in this case, we see that the relativistic corrections are 20%, and as theta varies, the corrections are more than 40% and even reach as high as 80%. The bright yellow part is just where the even part changes sign, and it is nothing interesting physically. Here we have some 1D plots. Both of these plots represent the ratio of the third order kernel, so T1113 and T1122, odd bit to the even trispectrum for a Euclid-like survey, which is on the left, and an SKA-like survey on the right as a function of scale. Both of these plots are for flattened configuration. In this case, we see that changing the viewing angles for the Euclid plot compared to the SKA plot changes the cancellations that happen between the third order kernel and the second order kernel. We can see mathematically that there are some interesting cancellations going on because the total T-odd is not equivalent to the sum of T1113 and 1122. We can also see that it is very heavily dependent on what survey we are looking at, because for SKA, the plots are quite different than the ones for Euclid. As we can see for this plot as well, here we have also plotted the same ratios. We have T-odd 1113, which is the third order kernel, and T-odd 1122 for the second order kernel. And we can see that for the Euclid-like case, the second order kernel contribution dominates for smaller values of k, while for the SKA case, we see that the third order contributions dominates for those values of k. We can also see that there is some interesting calculations going on here as well, because the T-odd value is much less than both the third and the second order kernel for the SKA-like case. As a conclusion, I would like to say that relativistic effects, they are naturally generating parity-odd signal in the observed galaxy trispectrum that manifests as dipole if you had to do a spherical harmonic decomposition. These contributions arise at order h over k, and because they are suppressed with respect to the standard redshift-space distortion terms, they have not been looked into past literature, but they become significant on horizon scales. The parity-odd amplitude also depends very strongly on geometry, redshift, and the bias of the tracer. And as we move on to an era with many surveys, it is becoming more and more essential for interpreting future survey data. Thank you.